Welcome. So we are discussing about uninformed search techniques. So in the last lecture, we have discussed about BFS, breadth first search, and uniform cause search. In this lecture, we'll be discussing about DFS, depth first search, and several other variants of depth first search. So basically, depth first search algorithm it proceeds in the depth fashion. That is, it will explore one path fully. It expands the deepest node in the frontier, and so the nodes expanded once the basically the leaf node. After expanding a node and identifying that that node is not a goal state, and if that node is a leaf node, then that node will be dropped from the frontier. That node will be dropped from the frontier, and the algorithm will back up the next deepest node, and it will create the unexplored successes, and it will explore the unexplored successes, and it will proceed. So the concept of depth first search algorithm, it is same as what we have discussed in data structures. If you have a graph or tree, something like this, then first it explores depth wise. After expanding a node, after during expansion, let us assume it checks for goal state. It expands. The last, say this is the leaf node. It checks whether this is a goal state or not. This is not a goal state. Now, when it expands this, it understands that this node does not have any child. Once one once after reaching a goal state, once after reaching a leaf node, and if that leaf node does not have any further child node, and if this is not the goal state, then this will be removed from the memory because no more this is required. Then again, the algorithm uh, will take the next node. Now automatically this node will be the top element in the frontier. Now this node will be further expanded if it has any other child. So if it has some other child, that will be expanded. If it does not have some other child, then again check whether this is the goal state. If this is not the goal state, now this is the leaf node. Now remove this. Again, now this node will be considered. So it has one node which is unexpanded. So the algorithm will go here and expand this. So if it has child, it will be expanded. If it does not have child, the algorithm will remove it. Okay, so this is the overall concept. And the frontier here, what we use is basically a LIFO queue. It's not a FIFO queue. If you recall, in the BFS, in the breadth first search, the frontier is a FIFO. It's a queue basically. It's a first in first out queue. Whereas in DFS, the frontier is LIFO. So basically, it's a stack. It's not a queue. It's a stack. So whatever the content which is entered recently, that is the one we'll be expanding first. So we'll be discussing with an example. By then it will be clear. So a stack can also be called as LIFO queue. Basically, it's a stack, or otherwise you can also call it as a stack instead of a queue. The stack can also be called as LIFO queue. Means the recently generated node is chosen for expansion. So without using frontier, also DFS can be implemented. That is, without using a stack, also DFS can be implemented. DFS can be implemented using recursive function call. That is, we keep on call a function. So recursive function is a function that calls itself. So basically, the recursive function call it keeps on calls the function for its child. So if you have a tree or a graph, something like this, then the algorithm checks whether first it checks whether this is the goal state or not. If this is not the goal state, then it calls the BFS algorithm on its left child. Then the left child checks whether this is the goal state or not. If this is not the goal state, then the algorithm calls DFS on its left child. So basically, the algorithm only checks whether the particular node is a goal state or not. If it is not a goal state, it will again call the same algorithm on its child. This process continues until it reaches the leaf node. After reaching the leaf node, there is no child. So automatically the algorithm will return. So where it will return in the sense it will go back to the column. So it will go here. Now once again this algorithm will call this on its other child. Because this basically it is not a one statement, it is a repeated, basically a while statement. While all childs, say you can say that while all childs not explode, not explode, the algorithm, what it will do in the sense, it will call recursively the DFS on the child, on the respective child. So first it has done for this child. So this child again it checks whether this is the goal state. No. Now it does not have any children. So it returns. After returning, this while loop will check whether it has more children or not. Yes, it has some more children. So again it will call on this. So in that way it continues. So the point is the DFS algorithm can also be implemented. The DFS algorithm can also be implemented without using frontier, with the help of a recursive function call that calls itself on each of its children in turn. And again, the DFS can be a graph search version or a tree search version. So already we have discussed about graph search and tree search. A graph search is one which will avoid the redundant paths, whereas the tree search will create redundant paths. Okay. So graph search version, it avoids repeated states and redundant paths. It is complete in finite space. Yeah. So what is this finite space? We are going to discuss the performance of DFS in different categories. We are going to discuss DFS in finite space and in infinite space. And also we are going to discuss its performance in graph search and also in tree search, in GS graph search and in tree search. So here we say that it is in finite space, it is complete. What does it mean? It means complete means, what is the definition of complete? An algorithm is said to be complete if it will find a solution, if a solution exists. That is, if a solution exists, then somehow it will find that. Such an algorithm is called as complete. Otherwise, it is called as incomplete. So basically, DFS is complete if the state space is finite. What is state space? State space means the set of states. So let us assume that for a particular problem, the DFS is having only a depth of 5. It is nothing beyond 5. So this is 0, 1, 2, 3, 4, 5. So always the solution lies, the graph itself, it has only a depth of 5, not beyond that. Okay. So this is a finite space. This is not an infinite space. So depth of 5, and you know the maximum number of children for each node. So you can identify maximum how many children are there. So in such cases, it will surely find a solution. So then it is optimal. But DFS is not optimal in infinite space. Infinite space means, say for a particular problem, you don't know what is the depth. The depth can be 100, the depth can be 1000, the depth can be 1 lakh. It depends. It varies. Depending on different instances of the problem, it varies. In that case, actually DFS is not complete because you have infinite space. And what happens? The algorithm may assume the solution is available in. There are many paths. But the DFS algorithm will first take the first branch, that is this path. Then it will go to the next path, so on and so forth. Say the solution is available. You have many paths. Say the solution is available in this path. in the fourth path. Say beyond this also there are many paths. Say the solution is available in this path, somewhere here at the third level. But assume this is an infinite tree. There is no end. There is no limit for this tree. Now the algorithm starts in this direction. It will keep on searching this line itself because this itself is an infinite path. It goes, and it never ends. So it will never come back, and it will never find the solution which is lying here. So infinite space, DFS is incomplete. So the tree search version, but the tree search version is not complete in finite space also. The graph search version is complete in finite search in infinite space, but it is incomplete in infinite space, infinite state space. Okay. But when you take the tree search algorithm, it is not complete even in finite space also, because tree search algorithm will allow redundant paths. So what happens? The redundant path may become a cycle. So for example, after the city A, you have B, and then C, and then A. Then it may cycle here itself, and this may become an infinite loop. It may become a never-ending loop. So even in a finite space also, if it is implemented using tree search version, it will become, it is, the algorithm is not complete. Find the tree search version. So to overcome this problem of tree search version of DFS, one thing can be done. So whenever a new state is created, we are talking about DFS in tree search now. So whenever a new state is created, that is whenever a new node is created, compare that node with all other nodes from the root to the current node. So you are creating a new node. Now compare this node with all other nodes from root to this node. So if already such a node exists, then don't create this node. Then don't include this node in the tree. By doing this, what we can do, we can try to make this algorithm complete. Okay. So by doing this, what happens? Infinite loop can be avoided. Because here tree search version, why it becomes incomplete? Because of the infinite loop. But whenever you create a new node, if you compare that node with all other nodes from the root node to the current node, and if any node matches this same node, then don't include this new node. If you do that, then infinite loop can be avoided. But still, you have to create these redundant paths. Okay, that is, the proliferation of redundant paths cannot be avoided. That is, still you have to create. After creating, only you have to check. So that will increase the complexity. Okay. In infinite state space, both versions fail if an infinite goal path is encountered. So in infinite state space, both the versions, the tree search algorithm and the graph search algorithm will fail to find a solution. That is, they are incomplete. They are not complete. In incomplete, in infinite state space, both versions, the tree search version and graph search versions, both are not complete because they may encounter a non-goal path, and this non-goal path is of infinite length. So they will keep on checking this path, and they will never come to the path where there is a goal. I think you are following. So basically, both versions are not optimal. The graph search or tree search, both are not optimal. So let us discuss one example. So yes. So this is a graph. Okay. So what we are going to discuss in this is, we'll be discussing this graph, how it is explored using DFS, that we will see. But before that, there is a drawback with DFS that we will address. the DFS algorithm may explore the entire left subtree even if node C is the goal node. Assume that C is the goal node. Assume that C in this tree, C is the goal node. Okay. But still, DFS, when it will come to come to C is only at level 2. But DFS will first explore all this path. Then it will explore this path. Then it will explore this path. Then it will explore this path. Then only it will come to C. That is, it will explore the entire left subtree. After that, only it will come to C. Right? So this is one of the major drawback with the DFS algorithm. Because of this, it is not optimal. Right? So it is the DFS is complete. I mean, in finite space, it is complete. But in infinite space, it is not complete in both the versions, in graph search and tree search version. And it is not optimal in both the versions. Whether you use graph search or tree search, it is not optimal. This is one reason. The another reason is assume that we have two goal states. Assume that we have two goal states. What are they? Let us assume that J is also a goal state and C is also a goal state. So where is J? J is here. J is here. So J is a goal state and C is also a goal state. Now the algorithm will give the solution as J. It won't give C. But actually C is the optimal solution. Because C is available at a least cost. So if you consider the level as the cost, here we are not associating any cost to the links. So if you consider how many levels the algorithm should pass or the depth at which the solution is available, if you treat that as the cost, then C is the optimal solution than J. But actually the algorithm, what it will do, first it will go here, then it will go here, then it will go here, and it will find J, and it will declare J as the solution. J is the solution, that is fine, but it's not an optimal solution. So because of these reasons, DFS is not an what do you call? Both versions of DFS were not optimal. Okay. So as we have discussed, if J were also the goal node, then that DFS would return that as a solution instead of C. But actually C is the optimal solution. This is the optimal solution. So this is another drawback. So basically DFS is not optimal, right? And the time complexity of DFS is order of b to the power d, which is same as that of BFS. And the space complexity is order of bm, where b is the branching factor and m is the maximum depth. Here m represents the maximum depth, okay, maximum depth of the tree, whereas d represents the depth at which the solution is available. D represents the depth at which the solution is available. So space complexity is not of exponential order; it is of linear order. Okay. So far, whatever we have discussed about DFS, it is mostly of negative information. Like DFS is not mostly. I mean, in infinite state space, both the versions of DFS, graph search and tree search, were not complete, and both the versions of DFS were not optimal. Then why should we use DFS at all? So far we don't have any clear advantage of DFS over BFS. So why should we use DFS? So the reason is space complexity. Actually, DFS has a very much reduced space complexity than BFS. So let us discuss this with an example. Assume that the nodes at the same depth as the goal node have no successors. That is, consider a tree something like this. Say this is the goal node, okay, and the nodes which are at the same level at the goal node, let us assume these nodes are at the same level as the goal node. Say they don't have any successors. That is, whichever the node is the goal node, that is the maximum depth of the tree. Let us assume like that. Okay. In that scenario, if you see, DFS requires only 156 kilobytes of memory instead of 10 exabyte at depth d equal to 16. So here I have drawn a tree of only of depth 2, but let us assume the depth of the tree is 16. Say let us assume the depth of the tree is 16 and the goal node is available at level 16. Okay, the point is the goal node is available at a depth 16, and let us assume the tree, there is no other further depth in the tree. That is which at which depth the goal node is available. At which depth the goal node is available, the nodes at those depth they don't have any successors. If we have that assumption, then DFS will require only 156 kilobytes of memory. But if you use BFS, it will need 10 exabyte of memory if the solution is available at depth 16. So this we have already discussed based on the chart. In BFS, if the solution is available at different depth, then how much memory will be required? So why such a reduced memory in DFS? Because in DFS, say assume that solution is this is the solution. Okay, but at level 16, this is depth 16, and let us assume this node is the solution. Now, what DFS does in the sense, basically, first DFS, what it will do, it will explore this path. Once it, after exploring this path, after identifying that this path does not have solution, it will ignore all these nodes. It will not keep these nodes in the memory. Then it will explore this path. After knowing that this path does not have a solution, then it will ignore all these nodes. This node will not be in the memory. Then it will explore this path. You're getting? So that its space complexity, you can see it is order of Bm. What is B? B is the branching factor. That is how much maximum number of nodes, maximum number of child a node can have, and M is the maximum depth. So at each level you are expanding. So when you expand this node, you get 2 child. If it is a binary tree, because branching factor is 2. If the branching factor is 5, you will get 5 child. But after that, you will explore this node only. When you explore this, if the branching factor is 5, another 5 will be created. When you explore this, another 5. Like that, it goes on up to the last level. So if there are 16 level, then, and if branching factor is 5, and if you explore this one path, then it will create only 16 into 5 nodes. Okay. 16 into 5 nodes, right? So that many nodes it will create. Then after knowing that this path does not have the child, then it will give up all these nodes. It will remove all these nodes from the memory. Then it will come to the next path, so on and so forth, it continues. So basically, it achieves a great reduction in space complexity. And that is the reason why DFS is most commonly used algorithm in the some of the AI applications rather than going for BFS. So there is another variant of DFS which is called as backtracking DFS search. It uses still less memory. So what this backtracking DFS, what it does in the sense, normal DFS, first it checks whether the root node is the goal state or not. If root node is not the goal state, then it expands the root node. It creates all its children. Even though it creates all its children, it will take only this part. Then it checks whether this is a goal state or not. No. Then it expands all its children. So here I am showing 2 children, but in reality there may be 10 children or 5 children or whatever it may be. Then it checks whether this is the goal state or not. No. Then it expands its children, so on and so forth. It continues. This is how normal DFS works. But backtracking DFS, what it does in the sense, it won't generate all child at a time. It will generate only one child at a time. So it checks whether root is the goal state or not. No. Then it explores only, it creates only the left child. It won't create all the child. So then it checks whether this is the goal state. No. Then it checks whether this is the goal state. No. Then it checks whether this is the goal state. No. Say let us assume this is the leaf node. So this is not the goal state. Then it removes this and it backtracks. Okay, then it checks whether this has another child or not. If it has another child, then it will explode. So on and so forth, it continues. So this algorithm actually it further reduces the space complexity. The normal DFS, the space complexity is order of Bm, whereas for this algorithm, the the space complexity is order of, it is only order of m, order of maximum depth. So yeah, it's order of m is the maximum depth. So I mean at each level we are generating only one node. So the worst case complexity is order of m. M is the maximum depth. So this is an improved version of BFS. So, right. So this is the introductory part. So let us discuss something beyond this. Yeah, let us try to understand the working mechanism of DFS. So this diagram basically what it shows in the sense. So this is the graph we want to search using DFS. So first we start with the root node. So first we check whether the root node is the goal state or not. If this is not the goal state, then explore, then expand the root node. When you expand root node, you get B and C. Now go to the left and check whether B is the goal state or not. Here we are checking whether B is the goal state or not. If B is not the goal state, then expand B. When you expand B, you get D and E. Then you check whether D is the goal state or not. If D is not the goal state, then expand D, we get H and I. Then we check whether H is the goal state or not. H is not the goal state, and H is the leaf node. That is, it don't have any other child. Now remove H from the memory. So you can see here H is removed from the memory. And the algorithm will backtrack to here, to D, to its parent. And its next child will be checked whether this is the goal state or not. No. This is not the goal state. Not only that, this is a leaf node. So again, this will be removed and go back. Now this is also the leaf node because you have removed this. So this is also leaf node. Now this is the goal state? No, this is not the goal state. So remove this and go back and go back. Now this node, does it have any other child? Yes, E. So go and check whether E is the goal state or not. So E is not the goal state. Now expand E. When you expand E, you got J and K. Again, check whether J is the goal state or not. No, J is not the goal state. As J is not the goal state and J is the leaf node, remove J and go to E. Does E has another child? Yes, K. Check whether K is the goal state or not. K is not the goal state and K is the leaf node. So remove K and go to E. Now E is also the leaf node and E is not the goal state. So remove E and go to B. Now B is also the leaf node because all these are removed. So B is also not the goal state. So remove B and go back to A. Now does A has another child? Yes, it has C. So you can see here when we move C, we have explored the entire left subtree, but it is also removed from the memory. So it's so this is how it maintains the space complexity. Now we check whether C is the goal state. No, C is not the goal state, so expand C. We get F and G. So now check whether F is the goal state or not. No, then expand F, you get L and M. Now when you check whether L is the goal state, no, but L is also a leaf node. It's not the goal, so remove L, go to F. And does F has another child? Yes, M. Check whether M is the goal state or not. So on and so forth, the algorithm continues. So this is the basic working mechanism of depth first search. Okay. So here is an interesting example. Where is that? Yeah. So this is another good example for depth first search. So this is using the frontier. But here frontier is a LIFO queue, or you can call it as a stack. Here frontier is a LIFO queue, or you can call it as a stack. Okay. So initially the frontier contains only E, the root node. Let us assume L is the goal state. So we check whether, so this is only in the frontier, we check whether this is the goal state or not. This is not the goal state. Then remove this from the frontier. Remove this from the frontier and expand it. When you expand, we get B and C. But here we enter this into the stack from right to left, not from left to right. In the Q case, we used to enter I think in which order we entered in Q. Yeah, in Q we entered left to right. Yeah, in Q also, in Q we entered left to right, but this end we assumed as head. So BC, so we did like this. Okay. But here in this algorithm, actually, we are entering from right to left because we want to explore B, and that should be at the top of the stack. We are using a stack, so that should be at the top of the stack. And when it will be at the top of the stack, it will be at the top of the stack only if it is entered to the stack at last. So we don't push into the stack like BC, but it will be pushed into stack like CB from right to left. First this will be pushed, then this will be pushed last. So if there are 4 or 5 children, it will be pushed in this order. First this, then this, so on and so forth. Right? So C is first pushed to the stack and then B is pushed to the stack. Now what's the top of the stack? B. So we check whether B is the goal state or not. Okay, so we are coming this way. Whether B is not the goal state, then remove B from the stack and expand B. When you expand B, you got E and D. Again, we push in this order. First push E and then push D. So we came here. Then check whether D is the goal state or not. If D is not the goal state, remove D and expand D. When you expand D, there is only one, that is H. So push H to the stack. So H comes here. Now check whether H is the goal state or not. H is not the goal state. So remove H, but we cannot expand. There is nothing to expand on H. So the algorithm, what it will do? Then remove what is the top in the element in the stack. It is E. So this is the goal state? No. So remove E and expand E. When you expand E, we got I and J, but it will be pushed as J and I. First J, then I. Then check whether I is the goal state or not. No, I is not the goal state. So expand I. When you expand I, you got M. So push M into the goal state. Now the top of the stack is M. So check whether M is the goal state or not. No, M is not the goal state. So expand M. But M does not have any children. So there is nothing to expand. So remove M. Okay. Then what's in the top of the stack? J. So then remove J. Check whether J is the, where is J? This is J. Okay. Check whether J is the goal state or not. No, J is not the goal state. So then expand J. But when you expand, there is nothing to expand. And J is already removed. There is nothing to expand. Then comes, now what's the top of the stack? C. So we finished all this path. We are coming here. So what we do? Then remove C from the stack and check whether this is the goal state. No, this is not the goal state. So expand C. When you expand C, you got F and G, but we push G and F. Okay. Then check what's the top of the stack. F. Is F is the goal state? No. So remove F. Expand F, but there is nothing to expand. F is already removed. Now what's the top of the stack? G. So remove G and expand it. When you expand it, you got L and K. Yeah, L and K, it will be pushed as L and K. And now what's the top of the stack? K. So remove K and expand K. Nothing to remove K and check whether this is the goal state or not. It's not the goal state. So expand K. Nothing to expand. Now what's the top of the stack? L. So remove L and remove L and X. Remove L and check whether this is the goal state or not. Yes, this is the goal state. So return this as the solution. So this is how the algorithm of depth first search works using the frontier LIFO-Q. So these are the things which we already discussed. That is the core reason why we are interested in DFS is because of its space complexity. Right? And we have discussed that by using backtracking search version of DFS, the space complexity can be further reduced from order of BM to order of M. There are also other concepts of DFS. So there is something called as depth limited search. So, so one of the major drawback of DFS is it is incomplete. It is incomplete. That is, it may not find a solution when a solution exists. So why this happens? Because the tree may be of infinite length. The tree may be of infinite length, but this problem can be rectified by using a technique. And that's what we are going to discuss. The failure of DFS in infinite search space can be prevented by giving a search limit here. Okay. So what does it mean? What does it mean in the sense? Assume generally the search space of a problem is infinite. That is, we don't know where is the that is we don't know the depth of the tree. It is of infinite depth. In that case, the algorithm says if that is the case, you fix a limit on the depth. You don't go for unlimited depth. You fix a limit on the depth. Let us say that we are fixing the limit of the depth as 10. Then the algorithm should go up to only the 10th level. So the depth for search, it goes like this. First checks the root, then its left child, then its left child, so on and so forth. It will go up to the 10th level. It will assume 10th level as the leaf node. It will assume the nodes at the depth of uh, 10 as leaf nodes. After reaching the leaf node at the depth 10, and after making sure that this is not the goal state, then it will backtrack. Then it will go to the parent and it will check whether the parent has other child or not. So like that, the algorithms, what you call the working mechanism is limited to a particular depth L. So if you do that, then that is called as depth limited search. So by doing that, what will happen? By doing that, what will happen in the sense, if the solution is available somewhere within this depth 10, then it is sure that we will find the solution. So that solution can be anywhere. It can be in this path or this path. It can be in any path. But still we can find the solution because we are not, the algorithm is now not going to follow an infinite path in which there is no solution. Okay, so that is the reason why DFS is incomplete, because it may follow an infinite path which does not contain a goal state, but maybe goal state in some other path in a very shallow deep level. So such issues can be avoided if we limit the search limit to L. So if you do this, then that algorithm is called as depth limited search. Okay, but again, in this case also we cannot say the algorithm is always complete, because sometimes you may fix a depth as 10, but the solution may be available at 15th level. Say there is no solution available at depth 10, so the solution is available at depth 15 only. So then also the algorithm fails. Unfortunately, it is not complete if we choose L less than D, where D is the goal node. Okay. Unfortunately, it is not complete. Sometimes this algorithm with a search limit L may not be complete. If we choose a limit L, if we choose a limit L which is less than D, where D is the depth at which the solution is available. In this case, what we have discussed, so the solution is available at 15, so that is D. But we have chosen L as 10. So again the algorithm will fail. So depth limited, so basically in most case, depth limited search is still not complete. Still it is not complete. Okay. And its time complexity is order of B to the power L. It's not order of B to the power D, because now we are limiting the search to level L. Okay, so it is order of B to the power L. Space complexity is order of BL, because everything is limited to depth L. Right? In the normal depth first search time complexity is order of B to the power D, because D is the depth at which solution is available, and space complexity is order of BM. But here we are limiting our search to level L or depth L, so it is order of B to the power L time complexity, and space complexity is order of BL. But in some cases, we know the depth limit. We know that the solution is probably available at this particular depth. Then this algorithm will be useful. So there is an improved version of depth limit search, which is called as So yeah, before going for that, this is an example for the depth limited search. So for this graph or for this tree, now we are limiting the depth to 2. We are not going beyond 2. And let us assume that G is the goal state. So let us see how this algorithm works using the frontier LIFO queue or stack. So initially the frontier contains A. So first we remove A from the frontier and we check whether A is the goal state or not. No, A is not the goal state. So expand A. First we push C, then we push B. So now the top of the stack is B. Check B is the goal state. No, B is not the goal state. So I mean first remove B, then check whether B is the goal state. No. Expand B, we got D and E. Push E and then D. So E and D. Now top of the stack is D. So remove D, check whether this is the goal state. No, this is not the goal state. Uh, so this is not the goal state. Now we won't explore D because our depth is limited to 2. What is our depth limit? 2. So already we have reached 2. So we assume that D is the leaf. So we assume because our maximum depth level is 2. We don't go beyond that. The algorithm don't go beyond that. So so after knowing that D is not the goal state, we don't explore D. Now once again the algorithm continues. Now what's the top of the stack E? So we check whether E is the goal state or not. I mean remove E and check whether E is the goal state. No, E is not the goal state. Now we don't expand E because E is also at level 2. So now what's the top of the stack? C. So remove C, check whether C is the goal state. No, C is not the goal state. So C is not the goal state. So expand C. When you expand C, what you get? Actually, here you should expand C. So when you expand C, you get G and F. When you expand C, you get G and F. Okay. So it will be pushed in what order? Yeah, sorry. First we push G, and then we push F. Okay. Here we are going to expand. So first we push G, then we push F. So what is the top of the stack? F is the top of the stack. Is F is the goal state? I mean, first remove F from the stack and check whether F is the goal state or not. F is not the goal state, but we don't explore F because F is at level 2. Now what's the top of the stack? G. So remove G and check whether G is the goal state or not. Yes, G is the goal state, so return G. Okay. So this is how the algorithm works, which is based on depth limited search. Here we are limiting the depth to a particular level. So that's the concept of depth limited search. So the depth limited search can be refined further. And so we get a next algorithm which is called as iterative deepening depth first search. So this algorithm is called as iterative deepening search or iterative deepening depth first search. So what this algorithm does? So this algorithm, what it does in the sense, initially it sets the depth as 0 and it calls DFS. In case of so in the previous version, depth limited search. In depth limited search, first itself we set the depth limit, like limit is equal to 10 or limit is equal to 15, like that. But in iterative deepening search, what we do in the sense, first we set the limit as 0. First we set the limit as 0. Limit 0 means only we are going to check the root node. If the goal state is not the root node, then you gradually increase the depth. Then you make the depth as 1. Okay. That means we are going to check up to the level 1. Then make the depth as 2. Then make the depth as 3. Then make the depth as 4. So on and so forth. Increase the depth. So that is what's shown here. So first we are going to call DFS with a depth limit of 0. That is, the algorithm will not go beyond 0th level. That is, it will check only whether the root node is the goal state or not. If root is not the goal state, then increase the depth. Now we make the depth limit as 1. Now we go up to this level. So if goal state is available in the first level, it will identify in the depth 1. If it is not available, then increase the depth to 2. Now if the goal is available somewhere in the third state, it will identify. Third depth, it will identify. Now increase the depth to 3. Now the algorithm, so if the depth is 3, first algorithm will go up to here. Then here, it won't explore M because depth is 3. Then this path, then this path, then this path, and then this path. So again, if the goal is not available here, now increase the depth by 4. Okay. So this is how this iterative deepening depth first search works. So this is actually a good refinement of DFS algorithm. But there is one critique on this algorithm, but actually that's not a serious issue. So what is in the so there is one disadvantage with this algorithm, but that disadvantage is not going to affect this algorithm much. So the disadvantage is the paths, certain paths are explored several times. Say for example, assume that M is the goal state. If M is the goal state, then first we check whether depth 0 or not. Is I mean whether we check whether whether goal is at depth 0 or no. Then when you go for second level, again second level also the algorithm starts from the top. So once again we check whether the solution is in depth 0. No, then only we check whether the solution is in depth. Solution is not, if the solution is not at depth 1, then we increase the depth level. Okay, then we increase the level. So now we set the level limit as 2. Now what happens? Now again the algorithm starts from the top. So now the nodes at depth 0, that is root node, will be checked 3 times. Nodes at depth 1 will be checked 2 times. Node at depth 2 will be checked 1 time. Now again, if these nodes, the solution is not available at depth 2, still the level will be further extended to 3. Okay, the limit will be the limit of the level will be extended to 3. So now we check whether the goal is in these nodes or not. But again, the algorithm will start from the beginning. Now the root node will be checked for 4 times. The nodes at depth 1 will be checked for 3 times. The nodes at depth 2 will be checked for 2 times. The nodes at this depth will be checked for 1 time. Now if goal is not available here, again the depth limit will be increased for here. Now once again the algorithm will start from the beginning, because always it checks from the root. So now root node will be checked for 5 times. The nodes at this level will be checked for 4 times. 4th time. This is the 4th time. First is during its own level, then during second, third, like that. And the nodes at this level will be checked for 1 more time. That is 3rd time. And the nodes at this level will be checked for 1 more time. That is 2nd time. And the nodes at this level will be checked for 1 time. So the point is, so as the depth extended, the nodes in the previous level has to be checked once again. But this is not a serious problem. The reason is we'll discuss this with an example. So this is the overview of the algorithm. This diagram shows clearly. So initially we set the limit as 0. So only root is explored. Then we set the limit as 1. Then all the nodes in level 1 is explored and checked. Then we set the limit as 2. Then all the nodes in level 2 is explored. Then we check the limit as 3. Then all the nodes in level 3 is explored. So on and so forth. So there is one critique with this algorithm, that is the nodes in the path has to be explored multiple times. If the goal state is if the goal is available at depth 5, then the nodes in the previous level of depth should be explored for multiple number of times. Okay. So, but this is not a serious problem. So that's what we are going to discuss in this example. So let us assume a tree with a branching factor of 2 and with a depth of 10. Consider it to be a full binary tree. That is, that is every node has 2 children. Okay, the branching factor is 2, so it's a binary tree, and depth is 10. Now, if you use IDS, that is iterative deepening depth first search, if you use iterative deepening depth first search, then what will happen? Then how many nodes, how many times each node, or the number of, say this node, the root node will be explored. When you use iterative deepening depth first search, the root node will be explored several times, because for level 0 it will be explored one time. When you increase the level to 1, it will be explored for 2 times. When you increase the level to 3, it will be explored for 3 times. Am I right? So 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 basically, if a node is explored for 2 times, then we assume that it is accessed twice. Okay, or it can be, you can also treat as accessing 2 separate nodes. How many times a node is accessed? How many times all the nodes will be accessed, or total node access? That's what we are calculating. So the number of access for IDS, iterative deepening depth first search, is the nodes at level 11, the nodes at depth 11. So depth is 10. So depth is 10. So depth is 10 means what? We are actually, root node is depth 0, and the one at the next level is depth 1. So actually the nodes at depth 11, depth 10 is actually, they are the 11th level. Okay, the level 11. Okay. So the nodes at the last level will be explored only once. So it is what? It is 11 into 2 to the power 0. It is 11 into 2 to the power 0. Right? Because these nodes will be explored only once. They are not going to be, we are not going to explore it more than once. Right? Yes. Whereas the nodes in level 10 will be explored 2 times. They'll be accessed 2 times. So it is 10 into 10. And the nodes in level 9 will be accessed 4 times. So it is 9 into 2 square. Okay, so on and so forth. The nodes at level 1. Okay, this is not the root level. The nodes at the level 1 will be accessed for 10 times. So 1 into 2 to the power 10. Okay, so 1 into 2 to the power 10. Yes. Okay. So I mean, so at level 1, if you see at level 1, we have, just a minute. Okay. See, for understanding, let us take this small graph, small tree. This tree has only 3 depth of 3, or level 3. Okay. So this is depth 0, depth 1, and depth 2. But actually we are numbering from 0, 1, and 2. But actually it has a depth of 3 or level of 3 if you number from 1 to 3. Okay. So now how many nodes are at the root level? We have only 1 node. So this can be represented. This is a complete binary tree. So this can be represented as 2 power 0. Okay. And at the next level, the node which immediately follows the root level, here which is represented as depth 1, here we have how many nodes? 2 to the power 1. Okay. And at the next level, we have how many nodes? 2 to the power 2. So on and so forth. Now you can increase the length of the tree also. If you have, so let us as the depth number is numbered as, the depth number is starting from 0 for root. So for the depth, if the depth is 0, then it is 2 to the power 0 number of nodes at this level. If the depth is 1, then we have 2 to the power 1, that is the number of nodes at this level. If the depth is 2, this is depth 2, then we have 2 to the power 2, number of nodes. So at the next level, we have 2 to the power 3 number of nodes, then 2 to the power 4, so on and so forth. Okay. Now the point is, so let me write neatly for more clarity. So let us assume the root is at depth 0. So at depth 0, the number of nodes we have is, sorry, at depth 0, the number of nodes we have is 2 to the power 0. At depth 1, the number of nodes we have is 2 to the power 1. At depth 2, the number of nodes we have is 2 to the power 2. Right? Okay. Now, if you use depth first search, all these nodes will be explored only once. It won't be, none of the nodes will be explored more than once. The nodes will not be explored more than once. It will be, every node will be explored only once. So the number of nodes, so the total number of nodes explored will be just sum of all these things. So that is 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2, which is nothing but 1 plus 2 plus 4. 4 plus 2, 6 plus 1, 7. Right? So if it is another depth, you can add. So depending on the number of depths, we can extend this calculation. But say we are using iterative deepening depth first search. If you use iterative deepening depth first search, then what will happen? Then the number of node, now our maximum depth is 2. As the depth number starting from 0, 0, the maximum depth is 2. So at the maximum depth level, the nodes will be explored only once. Okay. But before that level, before the maximum depth level, the nodes will be explored 2 times. Right? Before this maximum depth level, the node will be explored 2 times. So it is 2 into 2 to the power 1. This we can say 1 into 2 to the power 2. Whereas this is 2 into 2 to the power 1. And at the top level, and at the next level, it will be explored, the nodes will be explored 3 times. So it will be 3 into 2 to the power 0. So now, I mean, this node will be accessed 3 times. Each of this node will be accessed 2 times. So this will be accessed 2 times, this will be accessed 2 times. And each of these nodes will be accessed only 1 time. Okay. So now how many nodes are explored? If you consider this counts also as separate nodes, then at this level we have 4, at this level we have 4, at this level it is 3. So that value, how we can identify? So that we can identify like this. The nodes at the leaf level, at the last level will be accessed only once. So it is 1 into 2 to the power whatever the depth, plus the next level 2 into 2 to the power whatever the depth, plus the next level 3 into 2 to the power whatever the depth. You continue this process until you reach the until you reach the root node, which is at 0th level. So now we can calculate this. 2 to the power 0 is 1, which is 3, plus 2 2s are 4. Again it is 4. So it is 4 plus 4, 8 plus 1, 11. So it is same. So 3 plus 4 plus 4, which is 11. Right. So this is how we got these values. So now let us say that, now let us come to this point. B is equal to 2 and D is equal to 10. B is equal to 2 and D is equal to 10. So D, this is 0 D. This is next level. This is next level. Like that, we have up to 10th level. We have up to 10th level. Okay. Now in 10th level, at 10th level, we have how many nodes? So the numbering is from 0 to 10 only. This is 0th level. This is first level. This is second level. This is 10th level. At 10th level, we have how many nodes? At 0th level, we have 2 to the power 0 node. At first level, we have 2 to the power 1 nodes. At second level, we have 2 to the power, at depth 0, we have 2 to the power 0 nodes. At depth 1, we have 2 to the power 1 nodes. At depth 2, we have 2 to the power 2 nodes. So at depth 10, we have 2 to the power 10 nodes. And these nodes will be explored how many times? Only one time. So it is 1 into 2 to the power 10. Then the next level, we have how many nodes? 2 to the power 9 nodes, and they will be explored how many times? Each of them will be explored 2 times, right? Each of them will be explored for 2 times. So it will be 2 into 2 to the power 9. Okay. At the next level, we have how many nodes? At the next level, we have 2 to the power 8 nodes, and they will be explored for how many times? 3 times. So it is 3 into 2 to the power 8. Okay, right? At the next level, we have how many nodes? We have 2 to the power 7 nodes, and they will be explored for how many times? 4 times. So 4 into 2 to the power 7. Right? At the next level, we have how many nodes? 2 to the power 6 nodes, and they will be explored for how many times? 5 times. At the next level, we have how many nodes? 2 to the power 5 nodes, and they will be explored for how many times? 6 times. Okay. Plus 6, 5, 4, 3, 2. Yeah. At the next level, we have how many nodes? 2 to the power 4 nodes, and they will be explored for how many times? 7 times. At the next level, we have how many nodes? 2 to the power 3 nodes, and they will be explored for how many times? They will be explored for 8 times. And at the next level, we have how many nodes? 2 to the power 2 nodes, and they will be explored for how many times? 9 times. Okay. It continues until it reaches 2 to the power 0. So let me write that. Uh, so so at the next level, it will have how many nodes? Uh, so we came up to 2 to the power 2. At the next level, we have 2 to the power 1 nodes. And this will be explored for how many times? 10 times. At the next level, that is root level, we have 2 to the power 0 nodes, and that will be explored for 11 times. So that is how we got this value. 11 into 2 to the power 0. We have this 10 into 2 to the power 1. 9 into 2 to the power 2, so on and so forth. 8 into 2 to the power 3, 7 into 2 to the power 4, 6 into 2 to the power 5, goes up to 1 into 2 to the power 10. So when you use iterative deepening depth first search, and if the depth of the tree is 10 and if the branching factor is 2, then how many nodes, how many times the node should be accessed? 4083 times. Okay. But if you use just depth first search or breadth first search, this is applicable to BFS also. If you use just a BFS or DFS, then the nodes at each level will be accessed only once. Okay. So it is nothing but 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2, so on and so forth up to 2 to the power 10. So what is that? 2 to the 2047. So the difference is not that much. It is double. That's all. It is not, the difference is not exponentially high. The difference is only linearly high. So that is why we say that even though this is a problem, this is not a big problem. Even though this is an issue, this is not an issue to worry. Okay? Because it is not going to exponentially increase the complexity. So that's what we are discussing. So this is the same thing with branching factor 10 and depth 10. So if branching factor 10 means then at each level you have 10 children. Okay. So at the last level, then there will be 10 to the power 10 nodes. Okay, that will be explored only once. So 1 into 10 to the power 10 into 2 into 10 to the power 9 plus 3 into 10 to the power 8, so on and so forth. When you apply NDS, I mean iterative deepening depth first search, you got this many access to the nodes. But when you use DFS or BFS, you got only this many access. So that's it about DFS and its several variants. There is regarding this calculation, there is one more thing I want to show you. Yeah. So this is something like a formula we can use to calculate to identify the number of nodes an IDS will be generating. So if you feel whatever I have explained, if you are unable to follow that, then you can just use this formula. The number of nodes the IDS will be generating, it can be calculated like this: d into b plus d minus 1 into b square, so on and so forth. So this will continue, plus d minus 2 into b cube plus d minus 3 into b cube b to the power 4, so on and so forth, until when you do d minus 1, 2, 3, it should become until 1. So when it becomes 1, it will become b to the power d. So this is so here is another example which is quite straightforward. Say the branch factor is 10, depth is 5. So when you use BFS or DFS, at level 1, how many nodes will be created? 10 nodes. Here we are not considering the root node. So level 1, 10 nodes will be created. At level 2, 100 nodes will be created because branch factor is 10. At level 3, 1000. At level 4, 10,000. At level 5, 1 lakh. So total number of nodes generated is this many, leaving the what you call root node. If you include root node, another one will be there. Okay. So now when you use IDS, what happens? IDS, the root node, the leaf, the nodes in the leaf will be accessed only once. The nodes just above the leaf level will be accessed 2 times. Then the next level will be accessed 3 times. Then the next level will be accessed 4 times. Then the next level will be accessed 5 times. And the root will be accessed 6 times. So root, we have only one node. So if you want to include here root, then plus 1. If you want to include here root, then plus 6. Okay. Now this is same. This is going to be same for both BFS and IDS because these nodes were in IDS also it will be accessed only once. But these nodes will be accessed twice. So it will become 10,000 into 2, 20,000. These nodes will be accessed thrice. So it becomes 1,000 into 3, 3,000. These nodes will be accessed 4 times. So 100 into 4, it becomes 400. These nodes will be accessed 5 times. 10 into 5, 50. Okay. And root here will be accessed only 1 time, but here root will be accessed 6 times. So it will become 1 into 6, 6. So when you add these things, this is what you get. So the difference is not so huge. So it's a reasonable difference. So that is what we are discussing with this. So that's it about today's class. Let us stop here. Okay. Thank you.